Hello everyone, welcome for today's session. So today we're going to discuss on the semiconductor materials and their lattice structures and different types of lattice and their characteristic. Okay, so let's hit back to the screen. Okay, so as you all know, this the behavior of the atom. So even we have seen in the previous tutorial that the behavior of the atom and the wave function is entirely different when it is treated as the individual atom. But when the multiple atoms are brought closer together, their properties gets changed. So that is what we are going to see in today's and the coming topics or the coming sessions. So the semiconductor solids or the semiconductor electronic devices, mainly it concentrates on the electrical behavior of the solids, and we understand the transport of the charge carriers through metals or semiconductors. And also this behavior does not only depends on the properties of the electrons but also on the arrangement of atoms in the solid. So now let us talk about the semiconductor materials. So when we talk about the semiconductor material, so we know that the semiconductor, its property lays between a metal and the insulator. So the semiconductor property lays between metals and insulator. And we can control the flow of electrons, or we can control the movement of these free electrons with different mechanisms. So one is by temperature, second is by optical excitation, and third by impurity content. So with the increase of temperature, there are more number of free electrons that can be generated, and also with the optical excitation. Now, for example, if we expose a semiconductor to a optical light or maybe a sunlight or photon, so what happens? It will liberate again the free electrons. So maybe we can see this kind of behavior in the photodiodes and phototransistors. And impurity content means that the process of doping will increase the electrical property of the semiconductor. It means we are adding impurity atoms so that its electrical property gets improved by adding the more number of free electrons. So these are the three mechanisms which we can use in the semiconductor to liberate the free electrons, or to control the movement of the free electrons. To liberate the free electrons, in fact. Now, as we have seen in the previous tutorial, um, the periodic table. So now let us have a discuss on the different groups of the periodic table, and we will see the elemental and the compound structure of the semiconductors. Now in a periodic table, when we look into the group 2, so then we have the zinc, and we have CD, and in third group we have boron, aluminium, gallium, indium, and fourth group we have carbon, Si, and germanium, and fifth group we have nitrogen, phosphorus, arsenic, antimony, and then sixth group we have sulfur, then we have selenium, and we have tellurium, Te. Now, the semiconductor materials can be formed in a crystal if there are only the same type of atoms are brought close together. Now, if you look into this, the group 4, so this forms the crystalline structure or a crystal lattice. It means only the semiconductor atoms exist in that solid structure, and all the atoms are brought close together and form a crystal solids. But whereas that is not true for these cases, so for the then what we will do is that for group 3 and group 5 we will combine and we will form a compound structure. So those structures we call it as compound structures. Now let us look into the pure crystal solids. These we call it as elemental structures, that is Si and germanium, because all the atoms in this structure are silicon, and if we take germanium then all the atoms are of germanium. Whereas compound structures may be a combination of two types of atoms, that is silicon and carbon, and here the silicon and germanium. Then binary compound atoms, it might be a combination of third group and fifth group, so combination of third group and fifth group here, it will form a compound. So then we have a compound structure of aluminium and phosphorus. We have compound structure of aluminium and arsenic. We have a compound structure of aluminium and antimony. We have a compound structure of gallium nitrate. We have compound structure of gallium arsenate, compound structure of gallium and Sp antimony, and indium and phosphorus, and so on exist. So likewise we have another binary compound structure, so that is a binary of group 2 and group 6. If we form, then it is of compound structure. So it might be a zinc and sulfur, zinc and selenium, and zinc and tellurium, and so on. Okay, so these, the pure crystals are of same atoms, which are formed of same atoms, so those we call it as elemental structures. And if the structure is formed of different types of atoms, so then we call it as the compound structures. So if it is of two atoms, two different atoms, then we call it as binary compound structures, and so on. That combinations, you can see what are the different combinations that we can use in semiconductor devices. Okay, so now let us talk about the crystal lattice. Okay, so there are various types of crystal lattice based on the arrangement of atoms. How the atoms are arranged in the structure, based on that we categorize them into different categories. Now if the atoms are arranged in a very systematic way, and if the periodicity repeats, so periodicity means at every equal distance if the same atom is found, so such structures we call it as the crystalline structures. So this, let us call this as crystalline structures. And there are other structures where the atoms are very randomly arranged, there is no coordination and the distance between the atoms, and there is no periodicity between them. So such kind of structures we call it as the amorphous structures. So it is amorphous. These are amorphous structure. And there is a combination of these two, we call it as a polycrystalline, where if we take a structure, the entire structure is not periodically arranged, but the small area of it is periodically arranged. So this area is have one kind of periodicity. Maybe this area of the structure has another kind of periodicity of the structure, and then this region has another periodicity, and this region may have another kind of periodicity. So all together, if this is a one structure, so these kind of structures we call it as the polycrystalline structures. So polycrystalline structures, now that you also can see in this diagram. So this is a crystalline, this is amorphous, this is polycrystalline, and there is another diagram which helps you to understand the arrangement. So this is a single crystal, this is a polycrystal. You see this one group, and again there is certain gaps, and again there is one group. So there are multiple groups, but not all are connected to each other, whereas amorphous is very randomly arranged kind of structures. Now let us have a look at the characteristics of crystalline solid and amorphous solid. Then if you look into the characteristics, so here we have crystalline solids and amorphous solids. If we talk about the melting point, then the crystalline structure, since it is of same atoms, are arranged in a very periodic manner, so it melts at fixed temperature. So it has a fixed temperature, melting temperature point, whereas here it starts melting steadily or gradually. So it is melts steadily over a range of temperature. Second is the arrangement of constituent particles. So the arrangement here, it is regular, and here as we know it is irregular. If you see the next property, that is the shape. Here the shape is definite shape, whereas here it's again the irregular shape. And the separation between the atoms, so that we can call it as the cleavage. So when we cut this structure, then we have the smooth and plain surface. We get smooth and plain pieces of the two cut parts, whereas here it is very uneven and irregular shapes that we'll get. We'll get irregular shapes upon cut of structure. The cut of structure. Then fifth is the heat of fusion. It is definite, and here it is indefinite. And the sixth property is anisotropy. This is anisotropic, and this is isotropic. And seventh one is the nature of the structure. Here it is a true solid, and this is pseudo solid. Okay. So these are the basic characteristics of exactly, it's a various characteristics of crystalline solid and the amorphous, right? So now here the crystal structure is represented in a form of lattice, might be in a point representation in terms of the two-dimension representation of atoms in a form of lattice. This is for mathematical modeling. Now for example, if the atoms are arranged, the representation of these atom arrangement can be represented in a form of the lattice. So this arrangement we call it as lattice. Say this. This is a lattice structure or lattice arrangement of atoms, and each of these cubic here we call it as cell. So let me write the formal definition of the lattice. It is the periodicity in a crystal defined as symmetric array of points in space. Symmetric array of point in space is called lattice, right? So now here these lattice forms the basis vectors. So this, if we talk about this atom, then this is the one basis vector and this is the another basis vector which forms this entire lattice. So we will see one example here of the rhombic structure of the lattice. So this is a rhombic structure of the lattice where we have the atom here. So this is the basic vector A and this is the basic vector P, and if the same thing is shifted, if the same thing is the same point of atom is shifted somewhere else, then the same structure we can see here also. Same basis vector A and same basis vector B. So and this distance r can be represented as 3a plus 2b, because here if you look into the vector, if we see this point, so this is a 2 times the vector a and 3 times the vector b, and we reach to this point and still it forms the same kind of cell which we can see here, right? So now let's talk about the cubic, different types of cubic lattice. So there is a different types of cubic lattice. So we have 3 types of cubic lattice. One is a simple cubic, we call it as SC. Here the second one is the body centered cubic, we call it as BCC, and the third one is face centered cubic. Face centered cubic, it's not cube, let me write cubic, so we call it as FCC. So what are these simple cubic, body centered cubic and face centered cubic? Now let us see. Now if the atoms are arranged in this way, let me write the structure here. So then if we take one cube and if there are 8, sorry, this is supposed to be in a dotted form. Okay. If we take one cube, so the corners of this cube, there are 8 corners and the 8 corners are occupied by the 8 atoms. So then this kind of structure, if the same kind of cube pattern is repeated, then this kind of structure we call it as the simple cubic structure. This is SC. Whereas in a body centered it will be similar to SC, but there is a slight change, and the change is so let me write the BCC. So if you see the BCC, we have the similar kind of structure we can see here. Sorry, I'm not good in that drawing. Probably I think this line is not appropriate. So here, okay. So if you look at this and compare with this, then there is no difference, but the difference makes is that, so in a body centered cubic there is one center atom which is exists between at the center of this cube. So at the center of the cube is something like this which it shares. Yes. So this is called as BCC, the body centered cubic. Now face centered cubic is, let me write this face centered cubic with different colors so that we can make out, otherwise it's difficult to track, right? Okay. So one cube has this okay, right. So this is similar to simple cubic structure. There are 8 electrons, sorry, not electrons, my mistake. There are 8 atoms at the corner. So it is similar to SE. Now I'll choose the different color. Now let me choose this. And now if there is one atom at the face of each of this here, like this. Now here, this is on the back side, you can think of, and similarly here. So the 4 is over. Now let me choose the another color for the top and the bottom. So here we have one more on top like this, and one more at the bottom. So if there is one more atom at the phase of each phase of the cube structure, so then this type of structure we call it as FCC. So this is FCC. So now let us see how many each atom is shared by how many such cubic lattice in detail, so that we can understand this. Now in a simple cubic structure, what happens if the same pattern is repeated here, then each atom is shared with 8 cubes. So 8 cubes, so then this can be counted as 1 by 8. So then in case of simple cubic structure, in this case we can write the total number of atoms in one unit cell. Remember, the cell means we are talking with respect to this face is one cell. This is another cell. So here is the another cell. This is the front side is another cell. This is the another cell, and so on. Got it? So this is the unit cell. So then we have total of 8 atoms multiplied by each atom if it is shared, so it is 1 by 8, so it is 1 atom. So it means the total number of atoms in one unit cell in SC can be considered as 1 atom. Now let us see the total number of atoms in one unit cell in BCC. So in BCC what happens is that, so there are two things. One, as we have seen, every corner has 8 atoms, so 8 atoms, and this is shared by again 8 cubes. So then it becomes 1 atom. Then also it has one center atom, so 1 atom at center. So this is 1 into 1, which is equal to 1 atom. Now if we total this, then we have total number of, so here we can write the total number of atoms present per unit cell is equal to 2 atoms, right? Now if we see the total number of atoms for FCC, then it is, the theory applies the same. So we have 8 corner atoms, which is multiplied by 1 by 8 per corner atom, which is equal to 8 into 1 by 8, which is equal to 1. And the second is we have 6 phase atoms. So at each phase we have 6 face centered atom, which is again, it is, so if you look here, now if similar kind of atom if I write here, so one more cubic structure, and if I combine with respect to this phase, so what happens, this atom here which is in the center of the phase, it is shared with this atom, so it is shared with two cubes, so it is written as half atom per unit cell, which is equal to 3 atoms. So if we total this, we get 4 atoms in total. So we have a total of, or total number of atoms. So if I write the total number of atoms in unit cell per unit cell is equal to 4 atoms. Okay, so hope you've got this point. We will discuss about the diamond lattice structures and the extraction of these pure semiconductor or pure silicon from the silica process in the coming tutorial. So thank you for watching this session. So join us in the next session. Thank you.